Awesome. Well, thank you guys all for coming out and making it to the last talk of the day. It's been a jam-packed event, and I appreciate you all making it out here to learn about Dojo. I'm Tarrence, the co-founder of Cartridge and one of the core contributors of Dojo. And before we get started, I'll give you a brief introduction about Dojo, and hopefully throughout the talk, you'll understand a little bit more about how Dojo works, how we take advantage of the core affordances provability gives us in the context of on-chain games and autonomous worlds, and a little bit of the thought process and trade-offs and that allowed us to arrive at this solution. So before we get started, Dojo was a project that we conceived about a year ago, and it's really a community-driven project. It was started by 3 teams in the space that have a few years of experience building on-chain games in Starknet, and was kind of catalyzed by a transition in the ecosystem to a new programming language called Cairo 1, which is now just referred to as Cairo, which was a significant improvement. You may have heard in the past that Cairo was a very complicated language, and it was true. It was more like assembly language before, but the new version of it is very high level, and we'll see a little bit more about that in the future, in a little bit. So Dojo is an open source, provable game engine, and so as was suggested, the engine itself is written in Cairo, which gives us this property of provability, and it opens up a lot, significantly, the design space for building on-chain games and the amount of compute available to developers and the types of games you can build. So today we have quite a few different teams building on top of Dojo. Our team is building Roll Your Own. We have the Z Corp team that has been building some interesting games. Underdark, Starkland, obviously the Realms crew is all in on Dojo, building a bunch of different experiences on top of it, and some other teams like The Brick and Grugslayer and Beer Baron. And there's a bunch of other ones that I haven't put up here just because I ran out of space and logos. And as I mentioned, it's a community-driven project. So from the beginning, we really felt that Dojo needed to be a public good in order to achieve some of the properties that we want in autonomous worlds, this permissionless composability, extensibility. It really should be that the foundational layer of an autonomous world of an on-chain game itself is open to community collaboration, not owned by a particular entity, and can be contributed. And we've seen a lot of that over the past few months, with a lot of contributors coming into the ecosystem and starting to contribute in a bunch of different ways. We have a very thriving Chinese community, spearheaded by Taylor and some of the guys there. We have people coming into giving talks about Dojo now, onboarding new users, creating new repos, new primitives. It's really a lot of fun to see everyone coming to the community and starting to participate. So in this talk, I'll give you, we're going to hit a few different points. One is the provability is one of the core components of Dojo, and we'll talk a little bit about zero-knowledge proofs, how they work, and why they're kind of magical when it comes to what we're doing with on-chain games and autonomous worlds. We'll talk about the toolchain as it relates to the on-chain world, the contracts and the models that you use to define the worlds on-chain that enables this property of extensibility and composability. We'll talk about some of the off-chain parts of the toolchain, so the sequencing, the indexing, and the different clients that we're building, and then deployment of how you take a game from something that you're developing locally and put it into production, something that you can start playtesting with friends and eventually scale to large audiences. So we'll get started on the provability side. So Dojo leverages provability as a fundamental affordance, and it enables computational integrity, compression, and privacy. And it does that by basically allowing you to prove an execution that can be verified much more cheaply than it can be proved. And so you can prove some execution logic off-chain, and it can have this property of mathematical integrity through zero-knowledge proofs, and then verify it on-chain to unlock some outcome, rather than having to verify on-chain or the entire sequence. And we achieve this through the usage of Cairo. So Cairo is a provable programming language. It's a Turing-complete language. It differs from some of the other approaches that you may have seen for writing zero-knowledge proofs that are typically used, like CIRCOM or NOR, for writing application-specific circuits. In that Cairo implements a Cairo VM, which is a generic CPU built inside of a provable circuit. So you can write any language, any program inside of Cairo, and it could be executed on the Cairo VM. And it's a high-level language with traits, impls, macros, type safety. It's modeled after Rust, so it'll look very similar when we see that. The anatomy of a proof looks something like this. So this is the output of proving some computation. So when you for example, run some transaction inside of a sequencer or a sequence of transactions, at the end of the execution, you'll receive two artifacts. One of them is the proof. And so you can see like the proof computational complexity here is n times polylog n. So it's more expensive than running a native computation, but the verification is polylog n. So it scales very well as the computational complexity increases. And the proof size is around 45 to 200 kilobytes, depending on the size of the computation. And the other artifact that you'll receive along with the proof is a state diff, and this describes the state that changes in relation to the computation that was run. So in this case, you can see like some storage entries here with the key and the value were updated, and this zero-knowledge proof is going to attest to that computation that updated those. And so one of the magical properties of proofs is basically that because you can prove any Turing-complete language, you can actually implement a verifier in the provable language. And what that allows you to do is what's called proof aggregation. So you can take multiple proofs. So here you might have like multiple runs or different transactions, and you can verify them inside of another proof. And then you can have a single proof that can attest to all four of the outputs of this execution. And you have another interesting property that you can do this serially. So you have what's called proof recursion, and you can roll up these proofs, like some sequence of transactions, into a single proof. So if you have proof 1, proof 2, proof 3, proof 4, proof 5, like if you're familiar with, like, for example, optimistic rollups, in order to have an optimistic rollup to inherit like the security properties of the settlement layer, it has to basically checkpoint every single one of these transactions to the layer below it, which like significantly increases the cost of settling or the transaction execution. One of the cool properties of zero-knowledge proofs is you can forget about the entire history, because you can be sure of the integrity of the prior computation given the proof at proof 5 and the aggregated state diff that is attesting to it. And so if you combine these properties together, you essentially have some structure like this, which is what most zero-knowledge proof rollups are using in productions today, is this recursive tree structure where you can roll up a ton of proof, like of computational proofs, into a single proof that you then settle on chain. And again, you can forget about the entire history, so you end up with a single proof that attests to this massive amount of compute. In fact, it's like possible to attest to all of the provable computation that's ever happened with a constant size proof, which is a really incredible property. And as it relates to games, it's quite interesting for scaling games, especially session-based games. And then the last property that's quite interesting as it relates to games is this property of incremental proving. So when you're proving some computation, you can do it, as I mentioned, like proving is more expensive than native execution. So often it's not tractable for a client on a client device to prove like a complex computation. But you have this property of incremental proving, which can unlock this the privacy properties of zero-knowledge proofs, even for very expensive computations. So you can basically start doing a proof computation or proving some transaction on the client, and you can do what's called blinding the inputs, and that adds like the level of obfuscation that gives you the privacy component of zero-knowledge proofs. And then you can send it to a more powerful server that can continue the proving, can continue proving the execution without any knowledge of what were the inputs to that function. So it enables this property of hidden information or privacy inside of on-chain games. So altogether, these properties is what enables this pattern of fractal scaling, which is what we're building towards with Dojo. So with Dojo, you can think of basically the stack as looking something like this. You have some base layer of Ethereum. It's obviously like where we inherit the security of the entire stack above it. You have some global economy or state. And so in an analogy to like World of Warcraft, this would be like Orgrimmar or something, like where you want like global level state, maybe like the auction house, and probably where like a lot of assets will live, like ERC-20s and ERC-721s. Then you'll have regional rollups that are spawned close to users that allows them to have low latency to play inside of like a particular either geographical region in the real world, or even inside of a game, you can shard the execution into different locations. Like you can have, for example, like a shard just for the barons and you can decompose that so your users aren't competing for the same for compute in the same shared execution context and driving up transaction values as traffic increases. And then for like in a lot of games, you have much more isolated experiences. Like even if you think about like MMORPGs, a lot of the time in them is actually spent in instances that you're running with people. So you maybe have just 5 people in that instance, right? And there's no reason for every single person that's running an instance to execute that instance in the same context of everyone else. It's a self-contained event with a game or run with its own state. So it doesn't make sense to interact with the rest of the world. And with this architecture, we can spin up a sequencer or a Katana coprocessor that can run the series of transactions just for that run, and then it can generate a proof of the output of the run. So we don't have to worry about like how long the run was. All of the incremental steps of how the run went doesn't really matter to the rest of the world. All that matters is that you have some proof that attests to that you finished the dungeon run. You defeated like the final boss, and you can settle that onto the chain. You can attest to it. You don't have to. It has a nice property as well, where you don't have to leak information about like how you accomplished the run. You provide this mathematical proof that you were able to do it, and everyone is completely convinced of this fact, and you can unlock the loot associated with it. So this pattern allows us to scale like significantly the amount of compute that's available on chain, as well as significantly reduce the amount of state that is necessary to settle onto a data availability layer. You can just start thinking about like the outcomes of a series of events is what gets settled, rather than all the incremental states in between. So it opens up a lot of complexity and state inside of like a particular instance or dungeon run, for example. So that's a high-level overview of provability. We get the exponential compute through this execution starting. We get cheap settlement to Ethereum as O of 1 rather than O of n in the case of optimistic rollups. You get privacy through zero-knowledge proofs. You have better incentive alignment. So optimistic rollups are really great if you have a lot of people executing the shared context, but they make this like fundamental assumption that there's one honest actor. And so as you shard your computations and you have less participants, the security model starts to break down. So I think in those cases, Dojo can be a great complement to optimistic rollups and frameworks like MUD. Like you might, in a lot of cases, it might make sense to use Dojo for some piece of your game logic, although it could be used for any part of it, even to complement like some existing game that has other pieces that are implemented on optimistic rollups. And it has a better security model for alternative data availability, although the Redstone approach is quite interesting as well in that regard. And it has isomorphism. And so in Dojo, because we implemented the engine in Cairo, and Cairo can be executed in both the blockchain, it can be executed and proved on both the server side in the sequencer and proved like in large proving servers inside of AWS or GCP, but you can also do it locally. So you can take the same code that you've written for a game logic and execute it locally in the browser to get this property of privacy, and you don't have to do a context switch to a new language like CIRCOM or NOR or something like that. There are obviously some trade-offs around using a provable game engine versus something that's optimistic. Optimistic rollups they're coupled essentially to the binary of the sequencer, and you have a little more flexibility as far as like precompiles are concerned. You can push more logic into the sequencer itself. In a ZK rollup, everything has to be provable. Starks versus snarks, like Starks are larger in proof size versus a snark. Snarks are much more succinct, but snarks require a large key file on the client. So basically, if you wanted to use a snark versus a Stark for client-side proving, and in often cases with a snark, you have to download like maybe a 50 megabyte key file in order for someone to produce a proof. So it's a trade-off basically of like the upfront data that you need in order to produce a proof versus like what is the data that you send over the wire of the proof. And the Cairo VM is more expensive to prove than something like a application-specific circuit like CIRCOM or NOR, but it provides much better developer experience. So that's kind of like some of the properties that we get from provability that I think makes Dojo quite interesting for a lot of games that we're building in the ecosystem. I'll talk a little bit now about the toolchain and the different pieces that allows people to much more rapidly develop games on chain and start to experiment with the affordances that Dojo provides and try and build games for this aspirational goal of autonomous worlds. So we have Sozo, which is a toolchain for building and migrating worlds. We have Katana, which is our sequencer, a gaming-specific sequencer that can operate both as like a layer 3 or a coprocessor. And a coprocessor in this case is very similar to a rollup. It's just ephemeral, and it compresses state across the entire series of transactions. So it produces a single proof as the output, rather than like a rollup, which does like incremental checkpointing to the layer below it. Tori, which is our automatic indexer. Origami, which is a library of primitives that's actually built by one of the community members. Slot, which is a managed infrastructure service that we're building a cartridge. And World Explorer, that is a blockchain explorer built on top of the context of Dojo games, so onchain game explorer. So this is fundamentally what a Dojo world looks like. It's very similar. If you're familiar with MUD, it looks quite similar. You have a world contract that's a canonical entry point for the world. It provides us the property of composability and extensibility by allowing anyone to register different contracts or models with the world. So in the case of contracts, you could have low-level contracts like physics, you can have tokens, games, governance. So inside of a particular world, you may have multiple different games as entry points into that universe. And then with models, you have, very similar to a model in a database, you can have like avatars, items, balances, and different maps and stuff like that. And the primary purpose of the world is basically to serve as this canonical entry point. I think I have more. Yeah, there's a canonical interface for the on-chain world, and to allow this extensibility and composability through extension, and then to enforce some management access control across different components or different models in the world. So making sure that not anyone can write to anything in the world. There's some like permission logic around that. So I'll dig in a little bit about like what this looks like and practically in code. So this is a snippet of Cairo, and if you're familiar with Rust, it looks very much like Rust. Cairo has derives, so it's code expansion built into the language itself. And Dojo is a language plugin. So Dojo basically operates on the AST of your code before it gets passed to the Cairo compiler. Well, it's inside of the Cairo compiler, but we do like a pre-process on it that allows us to introduce new semantics into the language that makes it easier to build on-chain worlds. So in this case, you can see like we're deriving the model. Deriving the model basically sets up this property, this on-chain introspection property of Dojo models. So all of the type information that is inside of the struct is embedded in the contract itself. So you can fully introspect a model from the RPC, and you can rebuild the state of the world without having access to ABIs or the raw code. And that's what enables the auto indexer with Tori. And you can see this key annotation here that describes basically the ID of a particular entity or instance of this move struct in memory. So you can query this on the player address, and it's going to track how many moves are remaining. This is an example of the logic inside of a Dojo world. So this is an actions contract. Contracts are basically just regular smart contracts in StarkNet. You can see here we have the external modifier on the spawn function. Calling this function will just spawn a new user into the world. It's going to get the user's address. It's going to create an instance using the set macro here. It's going to create an instance of the player's movement state and the player's position state. And at the end of this function, like the user will be spawned into the world, and those structs can then be operated on. And this is very similar, a very simple move function here. The formatting got a little bit messed up, but what we're doing here is we're getting the callover function, we're getting their moves entity with this get function here, and then we're decrementing the moves remaining and then resetting it and updating that state. And so this, in this case, like this contract, this actions contract will need write permission to this model in order to update it. And so that's basically the language. It's very simple. There's some cool, more complicated stuff that we do with the generics and stuff that's supported by the language. We support like complex types in the models and deeply nested models. And there's some other new modifiers that we're introducing that enable some of the off-chain components of the toolchain to be a little bit more powerful. But this is the basics of it. And if you take a look at some of the starter packs or the tutorials, you can get up and running in a few minutes. So next I'll talk a little bit about the off-chain infrastructure of Dojo. So this is on the server side. So I'll start with the server side, and then I'll talk a little bit about the client side. So on the server side, the architecture basically looks like this. You have our sequencer Katana operating where you actually deploy your smart contracts and that handles the execution. Katana generates what's called a trace and a state diff that you can provide to a prover to prove the computation, and then the prover can checkpoint that to some settlement layer. Could be Ethereum, could be Optimism, could be any kind of chain, Starknet as well, or like further up in the fractal scaling kind of architecture. And then we have Tori server that talks to Katana over the JSON RPC. So we have a separation of concerns here because like Katana is a gaming specific sequencer, but actually Dojo is compatible with the base Starknet as well. So you can just deploy it into the regular Starknet world. And the Tori server will communicate to a world deployed on the sequencer over RPC. It'll use the type introspection to derive all of the types of the world and some events to rebuild the state of the world. And it generates a dynamic GraphQL and gRPC API. It's actually, the GraphQL part is pretty cool. It generates like a fully strictly typed GraphQL interface that is updated dynamically as models are deployed into the world. And the Tori server automatically handles that, has like full querying, pagination, and everything on it. And then the gRPC API, which is coupled to the Tori client, which is for higher throughput, more efficient communication, and that I'll talk a little bit more about in a second with the Tori client. And then eventually the plan is to also integrate an RTC stack for state channels and chat and those kind of requirements for games. So the first box that we talked about there was the Katana sequencer. So the sequencer, the job of a sequencer is basically to take some set of transactions and to commit to their ordering. And it can be done in a centralized fashion, like basically all the rollups today are centralized. It uses submit transactions, it sequences them, it commits to them, and then eventually it checkpoints it to some settlement layer below it. Katana is designed like specifically for Dojo games. It's centralized by design. It removes a lot of complexity of the sequencer. We have instant transaction inclusion. So we have, which is actually like a construct that a lot of ZK rollups are using right now, which is called the spending block. So you have one of the biggest challenges with high throughput rollups is basically the computational overhead of recomputing the state root very frequently if you want to have fast transaction inclusion. So we have this concept of a pending block, which is a block where a transaction is being basically soft confirmed into the sequencer, and you can update the game state to reflect it. And the sequencer has made a commitment that it's going to be included in the next block that's produced. So it allows us to give a soft confirmation much quicker, like basically instantly, similar to like Web 2. And then, a few seconds later, we'll actually produce the block with the computed state root and then start the proving process. And so one common misconception is like proving is expensive, so the sequencer must be slow, but actually the sequencer gets to execute just regular native code. And the proving process is done asynchronously with respect to the sequencer and can be like massively parallelized. So the proving overhead is not incurred during like the runtime execution of contracts inside of Katana. And then the end of a computation with Katana will produce a state diff that you can settle to the layer below. I mentioned that it can run in a co-processing mode, which basically means like, as I suggested earlier, you have like a massive like sequence of transactions, and you just have a single proof at the end of it that attests to the entire sequence. So it's like great for kind of like session-based games, like running a dungeon. And then you have the sequencer configuration, which is designed for persistent rollups, like maybe a game-specific layer 3 that you want to live forever, which checkpoints to like the settlement layer below it at some frequency. And then something else that we're working on in collaboration with some others in the ecosystem is secure enclave support for introducing hidden information into the worlds. We're planning to provide that with a very nice interface inside of Dojo. You can annotate different properties of the world that you want to remain private, and the Katana basically operating in the secure enclave will not expose that information unless like some predicate is met. And I think that's going to enable some interesting use cases for games. And so I'll show you this diagram again. This is basically the architecture that Katana is designed to run in. One interesting other thing I'll mention is with the proof aggregation, you can aggregate. A proof is not coupled to like a particular game, so you can aggregate proofs across like every single game. So the more games that are running inside of the Dojo ecosystem, the more proofs we can aggregate together, and we can amortize the settlement costs across all of them. And so the more popular your game is, like the cheaper it is for a particular user to interact with, which is like a great property to have, obviously. And so, we can drive transaction settlement costs like very low. Another interesting construction that's possible with Dojo is sovereign rollups. And basically what that looks like is instead of settling to a base settlement layer like Ethereum, you don't have to settle to a blockchain. And I think this is like one interesting construction for gamers, which are, a lot of the audience is kind of adverse to the hyper financialization the blockchain brings to the table. You can build games that can still live forever and can still be you can still decentralize like the backend infrastructure with Dojo by using zero knowledge proofs and data availability sampling, where you just like each particular player can verify a proof that attests to the entire history of the game and can verify that the state is available on some like data availability solution such as Celestia. On Tori, we have the auto indexer. It's stateless, so it's horizontally scalable. Like a sequencer is a stateful service, so it needs to operate. There can only really be one of them unless you have like some consensus layer implemented. So Tori server allows us to horizontally scale like the querying layer or the networking stack of Dojo worlds. It's verifiable, so the state of Dojo is a one-to-one transformation of the Merkle tree that exists inside the sequencer, so you can produce a storage proof that attests to any particular state inside of the world. It's typed through the onchain type introspection. It generates the GraphQL and the gRPC interfaces that I mentioned, and it provides streaming updates. This is a quick demonstration of like how we do the transform of the Merkle tree into the tabular database, and then generate a GraphQL typed query, and how we basically like the output artifact of ZK rollups is these state diffs that we can apply directly to the state tree to update the state. And then this is the client. The client is bound to the gRPC server. It's implemented in Rust. One of the nice things about that is we have C and WASM bindings and C# bindings. So we have the same core implementation of the client that includes things like optimistic updates that can then generate clients for all the different languages that want to interact with Dojo worlds, the clients for Unity and stuff like that automatically get all of that information, all the functionality that's included in the core automatically. Things like client-side proving that we're working on, or optimistic execution. And the last thing I'll mention is Slot, which is a managed infrastructure service. You can spin up Katana and Tori instances to play test like in seconds. You basically just need to run a single command and you get an instance ready to run in a couple seconds. A lot of the games in the Dojo ecosystem are using this today to play test their games. And then World Explorer, that is a block explorer for on-chain games. It looks kind of like this. We're going to more formally announce it at some point. And that's it. Thank you for joining us. We're going to... We're hosting a ninja school on Friday, which is going to be like a deep dive into the Dojo stack, some demonstrations of some of the games building on top of it. If you're interested in joining and aren't approved just yet, come reach out to me or Gabe sitting over there or Sylv over there, or anyone with wearing some Dojo merch. I'm sure they can help you out. If you want to learn more about Dojo, dojoedu.com. Cartridge.gg is the company that I run, or you can reach out to me at Tarrence at cartridge.gg. Given that this was one of the few infrastructure talks, the question that I'll leave you guys with is, what are the biggest gaps in tooling for developing on-chain games that you guys face today? Like, one of our goals with Dojo is really to abstract a lot of these horizontal concerns that every game is required to implement and allow us to more rapidly iterate with new experiences and explore the design space that's enabled by on-chain games. Thank you.